form. So we have here the companion matrix, and here we have the matrix with a lot of identity blocks in it, and the last block is just the leading coefficient here of the polynomial. Okay. And I called this pencil here the companion pencil. So there's a companion matrix and a companion pencil. So, but this is not the only way to rewrite this equation here of higher order into, bring it into a DAE of first order. There are other possibilities. And here is the second companion form. And here I only know how to do it if the leading coefficient is the identity matrix. So if somebody in the audience knows how to do it in general, please tell me. Yes, and there's a similarity between both companion matrices. And we talked a lot about Jordan chains and all this. Okay, I will not repeat this anymore. So, but there are three slides I have to discuss. And the first is the general solution formula if the leading coefficient is the identity matrix. So then we have a so-called monic matrix polynomial. So, and it's completely analogous to the scalar case we discussed to some extent. So suppose we want to solve our differential equation of higher order, and we have some initial values and inhomogeneous part here. Then this is the solution formula. So where the phi k's are now matrices, and all these matrices satisfy the homogeneous differential equation with certain initial values, namely that we have this relation that at time 0 the matrices are either identical or zero matrices. So this is this very nice solution formula, and here is again the method how to obtain these matrices. First of all, take the inverse of the polynomial, and then each element of the inverse is a rational function. And so you can perform a partial fraction expansion for each component of the matrix, and the result is then such a sum, where here we have again matrices now as coefficients. And if this is done, then we can find here the last, I would like to say the most important basis function by this formula. So replace here this denominator by exponential function times this polynomial part, so just the power of t. And then if this is found, then we can find the other basis function by differentiating this last one. First by differentiating the last one, and so we find the next, and then we can, if we have found the next, we can differentiate this and add a multiple of the last one, and so on. Okay, this is the method to find these basis functions, and then we have our nice solution formula, and everything is done. Okay, now some further remarks on matrix polynomials of second order. So I told you there are in principle two basic linearizations, the first and the second companion form. But there are a lot more. And here are some examples for, one could say, the most interesting case, namely that we have a differential equation of second order with a positive definite mass matrix, some damping matrix, and a stiffness matrix, and some right-hand side. So, and in applications, this is very often an external force. But in the formulas here, it does not matter whether these matrices have any special properties. So they don't even have to be symmetric or Hermitian. So, okay, we have this differential equation of second order, and we want to transform this to a differential equation of first order. And here are four possibilities. So the first one is just the first companion form. So you see here the coefficients are put in the lower row with a minus sign, and the leading coefficient appears here on the left-hand side. Okay, and here I wrote an I tilde because in the standard case this is the identity matrix, but you can put here any non-singular matrix. So this is in particular nice if you want to have some symmetry in these matrices. For instance, you can put here for the I tilde minus k again, or k, whatever you like. So next one, just reordering terms. We can move the c to the left-hand side. Yeah. Okay, and again we have here the freedom to take any non-singular matrix. Okay, and here are two further variants. Okay. But these are not all possibilities, and I found a very nice one in the book by Weselic. Okay, so basic idea is the following. Here's our differential equation again. So, and if now m, c, and k are Hermitian, or in the real applications real symmetric and positive semi-definite, then we can associate an energy with this differential equation. And it's, as you know from basic mechanics, the energy is the sum of the potential and the kinetic energy. So, but what is the kinetic energy? It's the squared velocity times the mass, and 1/2 of this. So in the matrix vector case, so you take the velocity from and multiply it from left and right with the mass matrix and take 1/2 of this. So this is the kinetic energy. And in the case of a simple spring, the potential energy is just this 1/2 of the square of the displacement multiplied with the stiffness. So, and here in the middle we have the stiffness matrix. You multiply this from the left and the right with the displacement. Okay, and take 1/2 of this. So this is the total energy. And then it follows from this differential equation that along a solution, the energy satisfies this equation here. So the time derivative of the total energy is minus this product here, and plus this scalar product of the external force with the velocity. So, and here the first term is a damping term, and the damping depends on the velocity. So the velocity vector is multiplied from the left and the right with the damping matrix. And this term here is the power supplied to the system by the external force. So So everything is as you expected. So this gives some additional energy, and here is an energy loss. So okay, and this is called a dissipation inequality, because so if this is a supply here, the energy change is not only given by the supply, but there is an energy loss. So okay. And now I found in the book of Weselic the following idea. If you look at it, it's very simple, but you must have this idea. So if K and L are, if K and M are both semi-definite, you can factorize them. So take the Cholesky factorization, for instance, or you can. There are a lot of more possibilities. For instance, you can have this equation here if you take for the L1 the square root, the positive semi-definite square root of K. Yeah. Or you can essentially, if you have such a factorization, you can multiply the L with any unitary matrix, and you get another factorization. Okay. So now you have this, and now you introduce new variables, not just displacement and velocity, but yeah, both of them multiplied with the L matrices. So, and then you make all these definitions here, and you get a very nice, yeah, at the end here, a very nice matrix. It has a lot of structure. So, for instance, if you multiply the last row with minus identity, you get a Hermitian matrix. And okay, so, and then you have an equivalent differential equation of first order. Y dot equals A times Y plus, so this is then the inhomogeneity. And yes, because of this factorization, the energy is just 1/2 of the Euclidean norm of the Y. This is quite trivial. So because if you multiply this vector with itself, yeah, you get a sum of two parts, L1 star L1 and L2 star L2. So, okay. And then if the external force is 0, then the time derivative of the energy, or now the Euclidean norm, is given by this formula. So here you have the damping. Yeah. Okay, and this is less equal 0 because the D is still positive semi-definite. So, and we have a minus here. And okay, this means with this new definition, the length of the Y vector is decreasing with time. But since the Y vector is given by Y vector at the initial time times the matrix exponential, you have also that the matrix exponential is decreasing. So, okay. Yeah. This is just to show you that there are many possibilities to transform such a polynomial differential equation into one of first order. Okay. So let's start with the next slide collection. So. Yes, and in this slide collection I discuss the basic equations in linear control theory, namely the Sylvester-Lyapunov and Riccati equations. And we will need a lot of what I say now in next week when we discuss optimal control. So actually here in this slide collection, there is a bit of optimal control, one slide, yeah, and a lot of about stability. Okay, first let's look at the general, it's a general Sylvester equation. So I define here the Sylvester operator, which maps a matrix to another matrix, and the matrices may be rectangular. They don't have to be square. Yes, and so the operator is given just in this way. A and B are fixed matrices. If X is a proper rectangular matrix, then A and B are square matrices of different size. So then associated with this mapping, we have two kinds of equations: an algebraic equation, so this term should equal some given matrix, or secondly, we have a differential equation. We can have that this matrix X depends on time, and then we can formulate such a differential equation. Okay, and if we now consider the algebraic equation, then we are interested in the question: does this equation have a solution? Does it have a unique solution? So, and we can ask this question over any field. So here K can be in principle any field. So in the case we are interested in, the field is the field of real or complex numbers. But what I will say now holds over any field. So the Sylvester operation is defined by these matrices, square matrices A and B, and if these matrices have co-prime minimal polynomials, so or say they have no common eigenvalue in an algebraically closed extension field of our field K, then the Sylvester operator is 1-to-1 and onto. So, which means that for any right-hand side C, we have exactly one solution. So, but that can be said a bit more. So, okay, there is a solution, but how can this be computed? So, it would be nice to have a formula. So, to compute the C from the data. So, and the data are A and B. So, and at least I can say that the solution of this equation can be written in this form. So, here is the right-hand side, and this is multiplied from the left and the right with powers of A and B. So, there is a polynomial, in fact, a polynomial in two variables. One variable is A and the other is B. And so the inverse is again a linear operator, of course, it has to be. And it can be given in this nice form. So, okay, and I'll give 3 proofs. So, now we assume that A and B have minimal polynomials which are co-prime. So, okay, yeah. Yes, then if these are co-prime and yeah, and I can prove, if I can prove from this that the inverse exists, yeah, it must be a polynomial. So, okay, I will show this in a minute. So, okay, we show that this map is in yeah, one-to-one. Yeah. So suppose so we have to check whether the kernel of this linear map is 0 or not. In other words, does the equation, the homogeneous equation, have only the 0 solution, or are there more solutions? So now, so suppose that we have a solution. So 0 equals ax minus xb. Then this means this relation. So, okay, and so now if ax equals xb, then I can multiply this from the left with a. So, and now ax equals xb, so I get xbb. So, and I can, okay, another notation, a square x equals xb square. And I can repeat this, so, and then I get this for any power. And if I have now a polynomial, then and I insert the matrix A into that polynomial, then I have just the sum of these terms. So this means for any polynomial, p of A times x equals x times p of B. Okay, this is the consequence. So so, and now I take a special polynomial, namely the minimal polynomial of the matrix A. So then this vanishes, and so, and then we have 0 equals x times mu A of B. But according to what I said in the first lessons, if the minimal polynomials of A and B are co-prime, then if we insert the B into the minimal polynomial of A, we get an invertible matrix. So the conclusion then is that x is 0. So, and this shows, okay, our Lyapunov operator is, yeah, 1-to-1. So, and it has to be then also onto because of the dimension of the spaces. So the pre-image and the image space are the same. No? Okay, and the operator is linear. If the kernel is 0, then it's bijection. Okay, this is the first proof. Okay, and in principle everything is done now. But I like to show also the other proofs. So we can think about our Sylvester operator as a difference of two very simple linear operators. So the first linear operator is multiplication with the matrix A, and I introduce for this this letter script A. And the same with B, but now from the right. So, and now these two operators, script A and script B, they commute. And this is a very trivial fact. So apply first the operator B and then the operator A. So then you get first x times B and then multiplication with A. Okay. But now, okay, but this is, yeah, or the operator script B applied to AX And yes, and okay, here you have it the other way around. So the script A and the script B are commuting linear operators on a space of matrices. So, and if you have commuting linear operators and you have a polynomial, you can insert these operators into the polynomial. Okay, we can do this in all cases. But now this makes sense now, because then if you make a calculation with these polynomials and this calculation has a certain result, then this result automatically also holds for the operators if you insert these operators into the polynomial. And the reason is the commutativity. So here, if you calculate with polynomials, you can exchange x and y, yeah, and get the same result. And okay, this is also the case for the operators, yeah, if they commute. So, okay. So the polynomial associated with the Sylvester operator is then just this. So we have a polynomial in two variables, and the first variable is yeah, A, and the second is B. So you can replace the here. So the polynomial is just x minus y, yeah, because then you can yeah, replace x by A and script A and y by script B. Yes, and now, okay, you have linear operators on a finite dimensional space, and these operators, you can rewrite everything as a matrix. So, yeah, you can make of this matrix X a long vector, and then the multiplication with the matrix A is again a larger matrix, which is multiplied with this large vector. But you don't have to do this. Just think about this. Okay, we have two linear operators on a finite dimensional space, and so we can then ask for the minimal polynomial. So yeah, or first we can ask for so for which polynomial is p of script A equal to 0? No? Yeah, okay. When is this the case? This is the case if and only if p of the original matrix times any x is 0, and this means that p of A is 0. So the script A and the matrix A, they have the same annulating polynomials, and so the minimal polynomials are also equal. Okay. And here now comes a non-trivial result. So if we have a polynomial in some commuting variables, yeah? And if these polynomials have no common 0, then there is a Bézout identity. Yeah? And this is in one variable, this is almost trivial. So but in several variables, this is a deep result. It's called Hilbert's weak 0 theorem, and it's on the basis of algebraic geometry. So this is yeah, fundamental there. Okay. So if we believe in this, so I will not give the proof of this. So if we believe in this, then we can consider now 3 polynomials: the minimal polynomial of the script A, minimal polynomial of the script B, and the difference polynomial. So and that these polynomials, that the minimal polynomials of script A and script b are co-prime, and yeah, this has as a consequence that these three polynomials have no common zero. So there are three other polynomials, phi, phi a, and phi b, so that this identity here holds. So, and now now we can replace our variables x and y with a and b, and then these terms here vanish. These terms here vanish. The third and the second, the second and the third vanish, and after the replacement, we have here our script a, here our script b, and here our a, and here our b. And on the left-hand side, we have the identity. So we get this nice relation here, and here this phi is a polynomial in a and b. So, and this is then, if we multiply it with our difference here, and this is the Sylvester operator, we get the identity. So this phi of script a and script b, this is the inverse of our Sylvester operator, and it's a polynomial. So, okay. So the inverse, oh, here the zero should be cancelled, so this is a relict from earlier notation. So there must be a polynomial which gives the inverse. Okay, this is, was an advanced proof. Okay, you may ask, this is very advanced here, the Hilbert zero theorem. Okay, if somebody is familiar with that of this kind of reasoning, this is the easiest way to prove everything. But if you hear it the first time, you think, oh, this is very, very abstract, and I don't really believe in this. I have not seen the proof, and but you can find the polynomial, the inverse, in another way, just working with only one, with polynomials in only one variable. So, and here's a simple way to do this. If the minimal polynomials are co-prime, so then by our Bibhas theorem in one variable, so there are polynomials LA and LB, so that this linear combination is the greatest common divisor of the minimal polynomials, and this, in this case, it is 1. So now we have these polynomials LA and LB, and from these we can define a new polynomial in this way. So, and this is indeed a polynomial here. Yeah, you might think, oh, isn't it just a rational function because I divide by this difference? But is not the case. So the numerator is such that each term here in the numerator is the sum of such differences here, and each of these is divisible by x minus y. So you get indeed a polynomial here. So, and then you calculate, multiply, take this polynomial, multiply with x minus y, and okay, I will not go to the details of the calculation, but the result is you have here some polynomial phi of x and y times the first minimal polynomial, and some other phi times the second minimal polynomial. And these phi's are made of the L's and the minimal polynomials, of the L's and the minimal polynomials. So this is just by reordering terms, you get such an expression. And now again, you have, if it comes to matrices, now replace the x with our script A and the y with the script B. Then all these terms here vanish, and here we have only the identity matrix, and this is a polynomial which gives the inverse. So, third proof is much easier. Yeah. Suppose our matrix B is upper triangular. Suppose first we are in this special situation. So, and we want to solve AX equals minus XB equals C. So, if we want to, okay, then we can write down these equations for the columns of C. So let's say C1 is the first column of the matrix C, C2 is the second column, and so on. So, and X1 is the first column of the solution. Yeah? So, and then we can take this equation and write the equation down column-wise. Yeah? And the outcome is then this sequence of equations. And if we reorder terms, we get another sequence of equations. And we see, okay, here is an equation for the first column of the solution. Yeah? So, and the question is, can this linear equation be solved? So it can be uniquely be solved if and only if this B11 A minus B11 identity is invertible. Yeah? Okay. So, but what is B11? B11 is one eigenvalue of the matrix B. Here on the diagonal, we then have the eigenvalues of the matrix B, and our assumption is that these eigenvalues are different from the eigenvalues of the matrix A. So then, this B11 being an eigenvalue of B is not an eigenvalue of A, and this means that this matrix is invertible. So we have a unique solution for the first equation. Okay, then we have this solution. We can put it here. And okay, and then again, we have an equation with an eigenvalue of B, which is not an eigenvalue of A. So we have an invertible matrix here, and we can invert, and so on. And so we can compute all the columns of X here, and this is unique, of course, as a result of the equations. So, okay, and this is now how we can solve this equation if B is upper triangular. But what can be done in the general case? In the general case, we have to transform this equation to an equation with a new B, which is upper triangular. Okay. So, and how can this be done? Yes. First of all, we can do the following. We can take the whole equation and multiply this from the right-hand side with the matrix T. You know, we can do this with any matrix. So then we have here the T here, and we have here the T behind the B, and we have it behind the C. And now we insert